Black holes and Einstein's theory of relativity, fact or fiction? Are science fiction authors crazy, or was Einstein truly so far ahead of his time? Everyone remembers seeing Einstein's infamous tongue-out drawing as a child and laughing. But even he admitted that some of this man's claims were too ludicrous to be genuine, making us adults laugh less. The theory of relativity is the one Einstein is most recognized for. Our knowledge of the cosmos and its functioning has been fundamentally altered by Einstein's theory of relativity. It demonstrated to us that time and space are relative concepts that depend on the viewpoint of the observer. The effects of gravity and speed, which are both relative to the observer, can now be incorporated into more accurate models of the cosmos. We are now able to explore and understand the universe in ways that were previously unthinkable. It has wide-ranging effects on science as well as on how we conduct our daily lives. Would you think that the GPS, or Global Positioning System, uses the laws of relativity to determine your precise location on Earth? We'll explore all the details of each science fiction book you've ever been obsessed with decoding at 3 in the morning, which is probably what drew you to this video. Both experts and laypeople have been astonished by the theory of relativity. In essence, it asserts that the universe is not as solid or absolute as it appears to be. Instead, it is always evolving, and the perception of time and space varies depending on who is experiencing it. This implies that two individuals who are present at the same events from disparate locations in the world may view them from entirely different angles. You wouldn't be far from mimicking just how insane it is if you closed your eyes and visualized a black hole, I can assure you. You will probably have the mental image of a massive, black spot in the sky that engulfs everything in its path. Well, it's not really that easy. Einstein's theory of relativity provides a justification for the existence of black holes, one of the universe's most interesting phenomena. When a large object, like a star, collides with its own gravity, a black hole is created. This mass accumulation produces a zone in space-time where gravity is so intense that nothing can escape from it, not even light. The event horizon, also referred to as the point of no return, is the boundary between the black hole and the rest of the universe. Above that point, the rules of physics effectively fail. The behavior of spacetime in the vicinity of a black hole is predicted by the general theory of relativity. Let's start by discussing how black holes impact space. According to the general theory of relativity, spacetime is bent around black holes, producing strong gravitational fields that can bend light. Because of the lensing effect this gravitational field produces, light from neighboring objects is bent and can focus on a specific region. This indicates that light from sources near the event horizon appears warped and focused into a specific area from the viewpoint of a viewer outside the black hole. An example of a gravitational lens is this. The light that escapes this gravitational field is also stretched, which causes it to seem redder as it moves further from the source. The term gravitational redshift refers to this, as it enables astronomers to investigate objects that may be too faint or far to be observed otherwise. Gravitational lensing has grown in popularity and significance. Similar to a lens you may use to read finer print on a piece of curious paper you find by the sea. You feel inquisitive, no? Astronomers are better able to investigate some of the most far-off, potent, and enigmatic things in the universe because they have a better grasp of how black holes produce gravitational lenses. Due to how this situation impacts the size and shape of the lensed images, it can be utilized to learn more about the characteristics of the dark matter that makes up most of the cosmos. Galaxy sizes and evolutionary paths can both be ascertained through gravitational lensing. Let's now discuss how it affects the passage of time. Do you know about the twin paradox? Two twins, one of whom traveled to space, are the subjects of the thought experiment known as the twin paradox. The twins discovered that the one who stayed at home was significantly older than the one who traveled when he arrived back on Earth. Do you anticipate that? I don't believe so. None of them did. So how is that even possible? Time dilation is the term used to describe this phenomena, and the theory of relativity helps explain it. Time can flow at different rates depending on the observer's perspective because, as we have mentioned, gravity and velocity have an impact on spacetime. The twin who traveled would have experienced significantly stronger gravitational pulls and faster speeds, which would have caused him to perceive time as moving much more slowly than the one who stayed at home. Time slows down at the event horizon in a similar manner and with a much higher gravitational force, literally coming to a standstill at the singularity, or the point of infinite gravity, at the center of the black hole. Coming back to the absurd twin dilemma, NASA made the decision to try the thought experiment on actual twins. As his identical brother remained on Earth, they sent Scott Kelly, an astronaut, on a year-long mission to the International Space Station. They gathered samples from the brothers before the experiment to compare with after the astronaut returned. The astronaut's telomere length, a DNA parameter linked to human longevity, had increased by 14.5% while he was on the International Space Station, according to a study of blood samples. The length of a person's telomeres at age 25 and their lifetime were shown to be correlated. Individuals with longer telomeres lived longer than those with shorter telomeres. I know, crazy, right? His telomere length was returned to normal 190 days after his return. Investigations are being done to confirm that the time dilation phenomena is what caused that to occur. The concept of a wormhole is another hypothesis related to the theory of relativity. Wormholes are imagined passageways in spacetime that link two far-flung locations in the universe. Theoretically, a wormhole might be utilized to reduce the distance between 2 points in the universe, enabling travel at a speed faster than light. A space traveler could utilize this to build a shortcut or even to explore parts of the cosmos that are too far away to be reached in a human lifetime. Although the existence of wormholes has not yet been demonstrated in reality, the relativity-based concept has captured the attention of numerous science fiction authors and space enthusiasts. Also, it's possible that a wormhole may be utilized to produce time travel, though this idea is still very much in the realm of theory. We can just write about it at this time. The general theory of relativity has so far stood up to every test that physicists have put it through. Our understanding of gravity, time, and space is based on this theory. It has taken the place of Isaac Newton's theory that gravity operates instantly and remotely. In addition, research on the cosmic microwave background has shown that many galaxies contain supermassive black holes that are millions of times more massive than the Sun. Hence, while it may be impossible to view the singularity of a black hole, its repercussions on the spacetime surrounding it may be examined, providing us with knowledge of this incredible and mysterious event. You must be wondering if there were any actual outcomes from the follies you have heard up to this point. The core of contemporary physics is Einstein's general relativity theory, which astronomers have been working to validate ever since it was first proposed. Sir Arthur Eddington, an astronomer, demonstrated that the sun's gravity can, in fact, bend light from stars during the infamous solar eclipse of 1919, as we had described in the gravity's effects on light. Gravitational waves have now been utilized in a new study to strengthen the case for general relativity. Little wavelets in spacetime known as gravitational waves are produced when two large objects, like as black holes or neutron stars, collide violently. The findings completely matched predictions from Einstein's theory, according to the study, which examined gravitational waves from a neutron star merger. This most recent study adds to the mountain of evidence showing gravity has the ability to bend space and time as predicted by Einstein's theory of general relativity. When the LIGO, Laser Interferometer Gravitational Wave Observatory, team spotted a signal from two black holes 2.3 billion light-years from Earth in 2016, they realized that black holes can merge. Two interferometers, one in Louisiana and the other in Washington, detected the signal, which was then further examined to determine its characteristics. The signal matched the characteristics of two black holes merging, and this was the first time that scientists had observed such a dramatic application of general relativity. The signal matched the expected behavior of two black holes orbiting one another and gradually inching closer to one another until merging into it. Further investigation revealed a phenomenon anticipated by general relativity but never observed before. The black holes were actually wobbling 3 times per second as they orbited one another. It turned out that the frame dragging effect was brought on by the black holes warping spacetime around them. The two black holes then began to sway as they circled one another as a result of this distortion. It is truly amazing and helps us better comprehend one of the most potent equations ever created, that two black holes can merge and wobble at a rate of 3 times per second as predicted by Einstein's theory of relativity. This provides us evidence that general relativity is correct, as well as that the universe is stranger and more enigmatic than we can ever fathom. The results of this study serve as a reminder of how much more there is for us to learn about the world and its enigmatic workings, and the possibilities linked with the theory of relativity are absolutely astounding. The theory of relativity is a crucial piece of information that will enable humanity continue exploring the cosmos and learning about its mysteries, whether researching the furthest reaches of space or talking about the potential of time travel. I appreciate you watching this video. I hope you had fun traveling with us. Don't worry, your telomeres are healthy. Don't forget to like and subscribe, and see you again soon.